For this big pictures in chemistry, I want to take a look at compound formation and in particular identifying different types of compounds, distinguishing between ionic and molecular compounds. And so this is something that comes up in a lot of different situations in chemistry, looking at combination reactions and trying to predict their products, writing net ionic equations, writing Lewis structures, which we do for molecular substances, but not usually for ionic substances. And so defined a compound here, and it's just a combination of more than one element in fixed proportions. I have two examples here, hydrogen combining with oxygen in a 2 hydrogen to 1 oxygen ratio. Of course, this is water, and water is an example of a molecular compound. Sodium chloride, 1 sodium for every 1 chloride, is an example of an ionic compound. And so what I want to do today is talk about why is sodium chloride ionic, why is water molecular, and why do compounds form in the first place, so that we can then use that to easily identify a compound when we need to in one of these situations. And then we'll look at a couple of examples of these situations at the end. So to start, I want to look at the periodic table, and we'll start with our tour of the periodic table with the noble gases. And of course, the noble gases are called noble gases because they don't react. And they don't react usually because they already have a very stable number of electrons. They don't want to add electrons. They don't want to take away electrons. They're in a very stable electron place. And so I like to call these the beach houses of the periodic table because elements that are there don't want to leave. Elements that aren't there want to get there. Okay? And so now we can break down the rest of the periodic table into two major groups. The first group are these elements over here and hydrogen. And these are what we'd call the nonmetals. Now the nonmetals are close enough, just a few electrons short of a noble gas, or they're relatively small and it's hard for them to lose electrons. And for nonmetals, their main strategy to get to the beach house, the main way they have to get to the beach house, is to gain electrons. Okay? We'll talk about some different ways they have to do that. For the rest of the periodic table, the metals, they are either a couple of electrons past or more than a noble gas, a couple of electrons more than the beach house, or they have a hard time, or they find it very easy to lose electrons. And so their main strategy for getting to a better place to get to a more noble gas configuration is to lose electrons. Okay? And so there's a couple different ways this can happen, but when a metal needs to lose electrons or a nonmetal needs to gain electrons, they can't just lose electrons to space or gain electrons from space. They need some partner to trade with. Okay? And so one very obvious arrangement is that if we put a metal that would like to lose some number of electrons and combine it with a nonmetal, we can make a compound, right? And the main result of this compound is that both the metal loses some electrons, the nonmetal gains those electrons, and they both get to their beach house. They both get to a noble gas configuration. Because the metal lost electrons, it ends up with a plus charge. Because the nonmetal gained electrons, it ends up with a minus charge. And this is what forms an ionic compound. Okay? For metals, that's really their primary strategy to get to a noble gas configuration and forming a compound. Nonmetals have another option, and that is if they encounter another nonmetal, they can share electrons so that both elements feel like they have more, right? And they both want to gain electrons. And so now they can share those electrons, and when they share, they make, in small groups, they make molecular compounds. There's some differences in structure and between ionic and molecular compounds. So an ionic substance has something that has a positive charge, something that has a negative charge, and then the cations and the anions, the positive charge and the negative charge, just arrange themselves so that in this continuous array. There's not any individual unit here. It's just a continuous repeating set of alternating charges. For molecular substances, smaller groups of atoms are sharing electrons, and they form individual groups. So like a water molecule is 1 oxygen with 2 hydrogens. For ionic substances, because there are no individual groups, we list formulas as lowest whole number ratios. For molecular substances, the formulas list everything in the molecule. So let's look at how we can use this when we're identifying, for example, if we wanted to write a net ionic equation. So here we have a double displacement reaction or a double replacement reaction, and we might be asked to write the net ionic equation for this reaction. Well, the first thing we have to do is figure out what ions are there, what ionic compounds are there. And so we need to look at each of these compounds and identify, is it ionic or is it molecular? So we might look at this one, sodium hydroxide. Well, sodium is a metal, and metals are present in ionic compounds. Here we have HF, hydrofluoric acid. Hydrogen is a nonmetal, fluorine is a nonmetal, so this is going to be molecular. And then come over to the product side, hydrogen plus oxygen makes water. Both are nonmetals, so this is molecular. Sodium and fluorine, the sodium fluoride. We have a sodium, that's a metal, this is going to be ionic. Okay. And once we know which compounds are ionic, we can break them down into their ions and continue the process. And this is sodium plus ion. Sodium always forms a +1 ion because that's what gets it to its beach house. Fluoride is a -1 ion. On this side we have sodium as a +1, and we have hydroxide as a polyatomic ion with a minus charge. Another example where we might want to identify, are we making molecular compounds or ionic compounds, is in combination reactions. And so when we look at a combination reaction between two nonmetals, the products are very difficult to predict. The sharing that goes on can take a lot of different forms, and those all can get the atoms either to or very close to their beach house, very close to their noble gas configuration. So when you combine nitrogen and oxygen, you might make this compound, NO, or this one, or this one, or this one, or this one. Okay? And so there's lots of different combinations, and that's going to be difficult to predict which one we form at this level. We need to know some more about the chemistry between nitrogen and oxygen to figure out under what conditions will which of these products form. Okay? We also need more descriptive names. We can't call all of these nitrogen oxides, so we have to call this nitrogen monoxide, dinitrogen monoxide, nitrogen dioxide, dinitrogen tetroxide, dinitrogen pentoxide. That's because there's so many different combinations between these. When we combine a metal like calcium with a non-metal like oxygen, the situation is different. Now we know we're going to make ionic compounds, and we're going to make the ionic compound that gets both elements to the noble gas, to their beach house. So for calcium, it starts at 20. Its beach house is at argon with 18 electrons, so it likes to lose 2 electrons and become calcium 2+. Oxygen likes to gain 2 electrons and become oxide 2-. And so the formula for the ionic compound that we make is calcium oxide. And that's the only compound between calcium and oxygen that forms calcium oxide. Ionic compounds, because of their repeating array of attractive forces, are generally solids at room temperature. Once we have that formula, then we can go balance the equation, but we can't even start to balance the equation until we predict the right formula. And we do that by using how many electrons does that atom or element need to gain or lose to get to a noble gas. Okay? So there's a couple of places where we can where we need to identify is a compound ionic and molecular, and hopefully now you have a better understanding of why ionic compounds form or molecular compounds form and under what circumstances.